great plains begin. At the 100th meridian. At the 100th meridian. Where the great plains begin. Driving down a corduroy road. We standing shoulder high. Sarah Street and its husky. Off in the distance. At the 100th meridian. At the 100th meridian. At the 100th meridian. Where the great plains begin. Haunted. Generation so much better than its parent. Came crashing through the window. A raven stays along the line of a road. Carrying somebody else down. The wires is so bad approval. Up down the distance. At the 100th meridian. At the 100th meridian. At the 100th meridian. Where the great plains begin. At the 100th meridian. 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 Where the great plains begin. I remember Buffalo, and I remember on the road. It would seem to me, I remember every single fucking thing I know. If I die of vanity, promise me to bury me someplace I don't want to be. You'll dig me up and transport me unceremoniously away from stolen trees, garbage bag trees, acts of enormity and lowness, slowly and sadly and robbery. You right through to sing my eulogy. At the 100th meridian. At the 100th meridian. Where the great plains begin. At the 100th meridian. 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 Where the great plains
All right. Good morning, everyone. Look, first of all, a lot of web work questions, apparently. You have to use the link on my courses. Use the link on my courses, and it logs you in automatically to web work. There is no username and password anymore. So that's one of the things that had to be ironed out. So everything's fine now. Log in through, so go to your My Courses, the 140 page, and then in the links section, you'll have a link to WebWork, and you're good to go. Now, people have logged in, have done that, and then gotten a 0 for the first assignment for WebWork 0. Don't worry about any of that. Don't worry about the mark that they give you for that assignment. That assignment is not worth anything. So do it, don't do it, whatever you want to do. Doesn't matter, it's up to you. Again, assignment 0 is only a tutorial on how the system works. Is there a tutorial on either Tuesday or Thursday? I'm sure there are. Minerva is your friend. Minerva will tell you. You should have signed up for a tutorial on Minerva when you registered for this course. Are we supposed to be using a calculator for the homework? Again, if the exams are in person, there will be no calculators allowed. So these types of questions will not come up, but you're certainly welcome to do them nonetheless. I mean, some of them have this little icon next to the question number that tells you have to use a graphing calculator or what have you. So nothing wrong with those. You know, I mean, the more you do, the better understanding you have. So, I mean, that's important in that respect. Where and how do we submit the web work if we need to do that? Well, that's exactly what the tutorial will tell you. So some of you have downloaded the questions. I mean, nothing wrong with that, but this is not how you submit the web work. Instead of downloading the whole thing, click individually on each question. There's a blue link. I mean, the question numbers are in blue, so it links to the actual question. Might be hard to see the first time you're doing it, but click on each individual question, and then there'll be, so the question will come up and there'll be space for you to, there'll be a box for you to enter the answer. Well, exactly. So assignment 0 is there. That's what you need to do. It's in the links, the web work link is in the links section on my courses in the content. So if you're on a computer, if you're on a desktop, click content, upper left-hand corner, and it'll bring you to the content business. If you're doing this on a cell phone, you have this box with 3 lines. Click on that and a menu will drop down. There is no time restraint on the individual questions. You are allowed to use a calculator to answer web work. My suggestion is to not do that and instead use web work as its own calculator. If the answer is root 2, you enter root 2. That's what the tutorial is going to teach you. I mean the assignment 0, I don't mean the actual physical tutorials for this course. You can complete the tutorial questions before going to the tutorial. It's always nice to do so. Or you can do them in the tutorial. I mean, it's up to you. Once you open the question on web work, you do not have to complete it. You can come back to it. As soon as you get 100% on a question, it has been recorded as such, and you're good to go. No time limit. I mean, except for the due date. You can have as many attempts as you want to get full marks. So anybody who does this seriously will get 100. There are about 6 or 7 web work in total, so about 1 every 2 weeks. I mean, from now on, tutorials started this week, so you've got, you should attend the tutorial you are registered for. Where do you find the tutorial questions? Again, everything is on my courses. All right, that's enough. Let's get back to work. Last time we introduced the idea of limits, right? A limit is the behavior of the function for values close to a, but not equal to a. We gave a definition, right? I mean, we said that the limit as x goes to a of x is L, if f of x can be made arbitrarily close to L by taking x sufficiently close to A. If your tutorial was on Monday, you may want to attend another tutorial this week. We're also working on having a tutorial recorded. So for those of you who are not in Montreal or in quarantine, so we're still working on that. Hopefully it's going to be ready by the end of the week. When will we have our first real web work? I like to open up the web work when we've covered all that material, all the material related to the web work, so that there are no questions and everybody's good to go. So probably next week. The tutorials are in person. Absolutely. Right, so we said that the limit as x goes to a of f of x is L if f of x can be made arbitrarily close to L by taking x sufficiently close to a. And, you know, we saw a lot of examples here. Right, if you look at the function x squared, and for any a, if you take values close to a but not equal to a, right? I mean, I should have mentioned that. If you take values close to a but not equal to a, the function is going to be close to a squared, right? And if you take the, you can make the difference arbitrarily close by taking x sufficiently close to a, but not equal to a. Here, the not equal to a doesn't really make a difference. But as we saw, if you had an open circle here, and your function defined as something else, it doesn't matter what your function is defined to be at the point A. This has no incidence on the limit, because we want close to A, but not equal to A. Let's take another function that you know rather well, function 1 over x. And here's the graph of that. And you see what is occurring as you get closer and closer to 0, right? As you get closer and closer to 0, the function is getting larger and larger in the positive sense, or more and more negative on the other side. This motivates the following definition. We say that the limit as x goes to a of f of x is infinity if f of x can be made arbitrarily large by taking x sufficiently close to a but not equal to a. Similarly, and let me not write it down explicitly, but limit as x goes to a of f of x is negative infinity. If f of x can be made arbitrarily large negative by taking x sufficiently close to a but not equal to a. Right, so we're defining what is meant for a limit to be infinity or negative infinity. An example, right, I mean, we have the graph right here in front of us, and as you can see, the limit as x goes to 0 from the right of 1 over x is infinity. And similarly, limit as x goes to 0 from the left is negative infinity. So these limits exist, right? One of them is infinity, and the other one is negative infinity. What do we mean by arbitrarily? Well, I mean as close as you want. Right? Remember, a limit is the behavior of the function. So what is the behavior of this function as x is getting closer and closer to 0, but from the right? That function is getting larger and larger, unbounded. Arbitrarily. And similarly on the other side, right? If you approach 0 from the left, the function is getting more and more negative. Let's investigate this more closely. Let's convince ourselves, right? I mean, what are we saying? If you're taking a number closer and closer to 0, this function should be getting larger and larger, right? I mean, we're just reading off the behavior from the graph, but as suggested, it's the opposite that we want to do. We want to be able to figure out limits in order to help us graph. So let's investigate the function 1 over x. For values very close to 0. If x is 1 over 10, what is your function? The function 1 over x is 1 over 10. You're dividing by a fraction, so you multiply by the reciprocal. And that's 10. And if you take something smaller than 1 over 10, maybe 1 over 100, you see what's happening? And by taking these values smaller and smaller, closer and closer to 0, the function itself is getting larger and larger without bounding. The function can be made arbitrarily large as you want, by taking x sufficiently small. Similarly here, right? If we look at the function 1 over x, if x is negative 1 over whatever, 1 over 3. So we have 1 over negative 1 over 3. And that is easily seen, right? I mean, you're dividing by a fraction, so you're going to multiply by the reciprocal. And that is easily seen to be negative 3. And if you take this, right, so negative 1/3 is going to be maybe here. And if you take something closer to 0, but still negative, so maybe negative 1 over 30. And so on and so on. You see how this is behaving. It's getting larger and larger negative number. And this idea can be generalized in the context of limits. If you have a limit that looks like 1 over, no, that's not what I want. 1 over 0. In the context of limits, 1 over 0 is going to be some sort of infinity. Let's think about that for a moment. I mean, it's never really 1 over 0, right? If your denominator is going towards 0, then you have 1 over a very small number. And this small number can be thought of as a fraction. 1 over something very large. So when you flip it, you get something very large. So in the context of limits, a 1 over 0 is going to be some sort of infinity. Definition, while we're here, y equals a is said to be a vertical asymptote of the graph y equals fx if y is a small number 1 over a large number. Well, I mean, you give me a small number, right? I mean, maybe 1 over 1,000 is very small. So it's really a fraction, 1 over something very large. Is there a way to tell when an x value becomes insufficiently close? That's an excellent question, Lucas. Let's hold off on that. Yes, you're right. Sorry. Thank you. Not y equals a, but rather x equals a is said to be a vertical asymptote of this if at least one of the following holds. Limit as x goes to a from the left of f of x is infinity. Or limit as x goes to a from the left is negative infinity. Limit as x goes to a from the right is infinity. Or limit as x goes to a from the right is negative infinity. Well, the small number is under 1, right? Because we had a 1 over 0 kind of business. But that small number can itself be thought of as another fraction, 1 over large, if you will. What is a vertical asymptote? Well, I'm defining it right here. I'm saying x equals a is a vertical asymptote if one of these limits, is valid. Now let's take this example to illustrate. Can the actual value be 0 or is it very close to 0? Right. Well, it's a limit, right? It's a limit. So the idea is if the behavior of the denominator is close to 0. So you never actually reach 0, right? And you know, this example illustrates the concept very, very nicely. Limit as x goes to 0 from the right of 1 over x. What do we want to do here? We want to describe the behavior of this function. As x gets arbitrarily close to 0, but never equal to 0. Because if it's equal to 0, we're in trouble. We've got a 1 over 0. This is undefined. However, the behavior of the function as x goes to 0 from the right is positive infinity. Right? I mean, we've convinced ourselves in a few different ways. One, from the graph, but also by plugging in values, right? 1 over 10, 1 over 100, 1 over 1,000. So this limit exists, absolutely. This limit exists, and it is infinity. Moreover, right, we have this. This, when x is 0, when a is 0 rather, right? This is that when a is 0, so x equals 0 is a vertical asymptote. We don't need to do any more to conclude that. If one of these 4 things is valid, vertical asymptote. I mean, we can continue on and we also have this, so we also have this one right here. So that would have implied vertical asymptote as well, but as long as one of them is achieved, that's all you need. We do not accept the notation plus and, well, I mean, it depends what you mean. You mean with a plus right here, that's fine. If nothing is mentioned, it's understood to be positive. Jasmine is suggesting that to figure out vertical asymptotes, we just need to figure out where the denominator is 0. That's, what shall I say? That's a way to figure out possible vertical asymptotes. There are no guarantees that just because the denominator is 0, you will have a vertical asymptote. You have to check using the definition, right? One of these limits should be either infinity or negative infinity. In other words, what's really going on here? Your function is blowing up near a vertical asymptote, becoming unbounded. Exactly. Somebody's suggesting that since these two limits do not agree, the limit as x goes to 0 does not exist. A very nice observation from last time. Let's take another example. This was only for the function 1 over x, but the idea of vertical asymptotes extends, right? I mean, we took the example 1 over x to motivate everything. But let's take another example, y equals ln x. You know the graph of this. And notice here that we don't have a denominator. So that idea of denominators equal to 0 doesn't quite work here. But you know the graph of ln x. right? You know the graph of ln x, and what can you say as far as the limit as x goes to 0 from the right of ln x is concerned? So if you take a function like 1 over x squared, limit from the left and limit from the right are both equal to infinity, and consequently the limit itself is equal to infinity. Correct. As everybody has suggested, this is going to be negative infinity, and consequently the definition of vertical asymptote is met, right? i.e. x equals 0 is a vertical asymptote of ln x. Absolutely. Why negative, Margot? Well, I mean, just look at the graph. What is happening here? This keeps going down and down. Right? Ln x being the inverse of the exponential. So for very large negative values, the function is close to 0. So very close to 0, the function has to be large negatives. But now the limit as x goes to 0 from the left, well, the domain here, this function is only defined on 0 to infinity. So it's not defined here, and consequently the limit from the left would not make any sense. When we get possible asymptotes, how do we prove them? Well, let's take a few examples, but our main tool, as I suggested, is the fact that in the context of limits, a 1 over 0 is going to be some sort of infinity. We're going to take that as a given, right? And I think we've convinced ourselves of that. If you're still not convinced, convince yourself. Right? Again, the idea is that we don't actually reach 0, but we're looking at numbers closer and closer to 0. And depending on whether these were positive or negative, the whole thing is going to be either positive or negative. Let's take a few examples. Let's illustrate with some examples. This is taken from page 92. We are asked to determine the limit without graphing the actual function. If there's no limit from the left, can we say the limit exists just based on the limit from the right? No. No. In that case, you would only restrict your attention to the limit from the right. Period. There would be no need to talk about the limit in general because the limit from the left does not make any sense. So for a limit to exist, does there need to be a defined function? Absolutely, right? And in the definition of the limit, remember that we needed f to be defined near a. So if it's not defined on one side, then that's completely out. For a limit to exist, so if I drew a line that arbitrarily becomes steeper at random points as it approaches 0, so as to approach infinity, would a limit exist? Well, I mean, if you're talking about, I mean, we saw an example, right? Something like this, y equals 1 over x. Or maybe you want the same on both sides. Somebody had mentioned 1 over x squared. So a limit from the right is infinity. Limit from the left is infinity as well. So limit as x goes to 0 exists and is infinity. You've been looking at, people have been answering this question, right? I mean, if, first of all, these are two lines, right? I mean, two linear functions, very well behaved. You know the limits of both of these exist. And we're not going to graph what this looks like, but you know that it's made up of two very well behaved parts. As x gets closer and closer to 5, you recognize that the denominator is getting closer and closer to 0, whereas the numerator is getting closer and closer to 6. So this is going to look like a 6 over 0. I'm not going to write that down, but it looks like a 6 over 0. And in the context of limits, whether it's 6 over 0 or 1 over 0, it doesn't make any difference, right? You're going to have a 1 over 0, so this is going to be some sort of infinity. You have to determine if it's going to be positive infinity or negative infinity, right? The denominator gets closer and closer to 0, so you're going to have a 6 over a small fraction, and that small fraction, you divide by that, so you multiply by the reciprocal, it's getting larger and larger. Is it positive or is it negative? Well, the numerator is going to be close to 6. You know that. It's just a straight line. The numerator is going to be close to 6, so that's positive. Denominator, again, just a straight line, but x is less than 5. So a number less than 5 minus 5 is going to be negative. Numerator is positive, denominator is negative, the whole fraction is negative. Why is it positive infinity and not 0? I'm not sure where you're getting that from. How about limit as x goes to x of x to the x? Well, that's just going to be x to the x. I mean, there's nothing, there are no values there anywhere. We're just looking at the behavior. So first of all, these are two straight lines, right? You have y equals x plus 1. So that's just a straight line. And you know, I mean, very well behaved. And as you approach 5, you know that this is getting closer and closer to 6. So that's all good. And if we look at x minus 5, this looks like this. Again, a straight line, very well behaved. And as x is getting closer and closer to 5, you know the function is very close to 0. So if we're approaching 5 from the left, here you'll be in a negative region for x minus 5. Here you're in a positive region for the numerator. So numerator is positive, denominator is negative. So the whole fraction is negative. But as x goes to 5, this has the form 6 over 0. Right? So in the context of limits, there's going to be some sort of infinity. All we need to do is determine if it's positive or negative. Numerator is positive, denominator is negative, the whole fraction is negative. It's infinity because of this idea in the context of limits. A limit that has the form 1 over 0 is some sort of infinity. I know there's still some confusion. Let's postpone me answering questions for a moment, and let's consider some limit laws which will perhaps convince you. Suppose you have two limits that exist. Limit as x goes to a of f and limit as x goes to a of g both exist. Then the limit of the sum exists, and it's equal to the sum of the limits. The limit of a product exists, and it's equal to the product of the limits. The limit of a quotient exists, and it's equal to the quotient of the limits, assuming the limit of g is not 0. One, two, three, four. The limit of a power exists, and it's equal to the power of the limit. If c is a real number, the limit as x goes to a of c is c. The limit as x goes to a of x is a. And 5, 6, 7. If f of x is equal to g of x for all x not equal to a, and the limit as x goes to a of f of x is the same as the limit of g of x. Let's prove a few of these I'll give you a moment to write those down. Let's prove 5, 6, and a corollary. Proof of 5. Let's see be a real number. And look at the graph of y equals c. We know what that looks like. It's just a horizontal line. So as you are getting closer and closer to a, the function is getting closer and closer to c. That's it. Limit as x goes to a if c is c. Repeat for 6. In fact, I think we already convinced ourselves of that last time. Look at the graph of y equals x. Can we explain number 4? All it's saying is if you're taking powers of a function, you can take the limit of the function and then raise it to the power. We'll take an example of that right after we look at 6. We've graphed y equals x. So look at values near a. Well, at a, the function is a. And for values close to a, it's still close to a. And we're done. Limit as x goes to a of x is a. It's the behavior of the function. Law 7 says that if f and g are equal to each other, close to a, but not necessarily at a, then the limits will be the same. Right? I mean, you know that the limit, you know that what the function is at a has no incidence on the limit. So if the functions are the same everywhere except perhaps at a, then the functions must behave the same for all x not equal to a. Can we show 7 on the graph? Well, take two functions that are the same everywhere except at a. So one function might look like this. The other function has to be exactly overlapping the first one, except maybe at a. So their behavior, as you get closer and closer to a, without ever reaching it, must be the same. Somebody was asking, what about the other rules? We'll prove the other rules a bit later. But right now, what I want to bring your attention to is what happens if you have a polynomial. If p of x is a polynomial, we're not skipping ln. Ln is a Very. Very important function. So if p of x is a polynomial, then the limit as x goes to a of p of x is p of a. Corollary. It means it's something that follows from these limit laws. Right? So if you have a polynomial, the limit of p of x is p of a. So first of all, let's prove that, if you will. What does a polynomial look like? I mean, you know examples of polynomials, right? Somebody give me a polynomial. X squared minus 3x plus 1. This is a polynomial. And, you've got other examples. Well, I mean, let's prove it with this polynomial here. Let's prove it with this polynomial. And I'll let you generalize. I'll let you generalize to any polynomial afterwards. So what is this limit? I want to leave the limit laws there. By the first limit law, the limit of a sum, or difference, of course, is let me break it up like this. Right, the limit of a sum is the sum of the limits by property 1. Right, so this is by 1. And now, the limit of a power, and somebody was asking about that, right? The limit of a power is the power of the limits. Here, limit of a product is the product of the limits. And here, limit of a constant is that constant. So this is by property 4 and by property 5. By 4 and 5. Let me run these off now. Also by property 2, limit of a product. And now, by property 6, limit of x is a, so this is a. By property 5, this is minus 3. And this, by property 6, is a. And that's just 1. So we get a squared minus 3a plus 1, which is the function, right? Which is this polynomial evaluated at a. Right, so this is p of a. And this is true for any polynomial. In fact, by property 1, 2, 3, for the quotient, if R of x is a rational function, and A is in the domain, the limit as x goes to A of R of x is R of A, where a rational function is one polynomial divided by another. Why go through these calculations rather than just plugging in as the x value? Well, how do you know you can plug in as the x value? You know because of these limit laws. That's the thing. It's these limit laws that will allow you to plug in for polynomials and rational functions. Exactly. Exactly that. Corollary. COR means corollary, something that follows from the limit laws. Well, we're done. We're done for the day. It's time to finish anyways. All right. So, I mean, you can have a look at page 102, where you'll have more of these kinds of examples where they want you to evaluate limits using the limit laws, justifying at every step what you're using. So have a look at these, and we'll pick this up again on Friday. Thank you all for coming. And we'll see you then.